Hello there, and welcome to The Sleepy Scientist, where wonder meets wandering, and space science takes the scenic route to slumber. Tonight's gentle journey carries us to the edge of discovery, where the James Webb Space Telescope has captured whispers of something extraordinary, a planet that may rewrite everything we thought we knew about worlds beyond our own. But before we drift into the cosmic depths, I'd love to know where in the world you're watching from and what time it is in your corner of the night. Fitting, isn't it? A video about distant worlds, and here we are scattered across our own small planet, each of us gazing upward at this very moment through our own slice of darkness. If you find this voyage soothing, intriguing, or just a peaceful way to unwind after a long day of earthbound adventures, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of cosmic calm reach others who might need a gentle pause beneath the stars. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something about the magnificent universe we call home before drifting off. So settle in, slow your thoughts, and let's begin. Because somewhere between starlight and speculation, between data and dreams, lies the story of a discovery that's making astronomers around the world lean forward in their chairs and whisper, "Could this be the one?" Imagine for a moment that you're an astronomer peering through the most powerful telescope humanity has ever built. Your eyes trained on a point of light so distant that its photons have been traveling for centuries just to reach you tonight. You're searching as countless others have searched before you for signs of something familiar yet impossibly far away. A world that might harbor the conditions for life as we know it, or perhaps life as we've never imagined it. And then, in the cascade of data streaming back from space, you see something that makes your breath catch something that doesn't quite fit. The patterns you've memorized, the comfortable categories you've learned to expect. This is the story of one such discovery, a planet designated K2-18b that has captured the imagination of scientists and dreamers alike, because what the James Webb Space Telescope has revealed about this distant world challenges our understanding of where and how life might emerge in the universe. K2-18b orbits a red dwarf star called K2-18, located about 124 light years from Earth in the constellation Leo. Now, 124 light years might sound like a manageable distance in the grand scheme of the cosmos. But let's put that in perspective. If you could somehow travel at the speed of light, the fastest anything can possibly go, it would still take you 124 years to reach this world. That's roughly 5 human lifetimes of constant travel at a speed that would make you a streak of pure energy. The photons of light that left K2-18b when the James Webb Telescope observed it began their journey sometime around the year 1900, when Queen Victoria still ruled the British Empire and the Wright brothers were just dreaming of flight. But distance is just the beginning of what makes K2-18b remarkable. This planet sits in what astronomers call the Goldilocks zone, or more formally, the habitable zone around its star, not too hot, not too cold, but just right for liquid water to exist on its surface. It's a phrase that sounds almost whimsical, doesn't it? The Goldilocks zone, as if the universe were telling bedtime stories about bears and porridge. But the reality is far more profound, because liquid water, as far as we know, is the essential ingredient for life, at least life as we understand it. Every drop of water on Earth, from the vast oceans to the morning dew on your windowsill, tells the same story that where water flows, life has a chance to flourish. K2-18b is what scientists classify as a subneptune, a type of planet that doesn't exist in our own solar system. Imagine a world larger than Earth, but smaller than Neptune, somewhere in that mysterious middle ground with a mass about 8.5 times that of our home planet. If you could somehow stand on K2-18b, you'd feel the pull of gravity much stronger than what we experience here on Earth. Though whether you could actually stand on anything solid remains one of the delicious mysteries we're still unraveling. The planet completes one orbit around its red dwarf star every 33 Earth days, which means a year on K2-18b would flash by in little more than a month by our reckoning. Red dwarf stars like Ku-218 are fascinating cosmic characters in their own right. They're smaller, cooler, and dimmer than our sun, but they have something our sun lacks: incredible longevity. While our sun will burn bright for about 10 billion years, red dwarfs can keep shining for trillions of years. Some of the red dwarfs burning today will still be glowing long after our sun has swelled into a red giant and faded to a white dwarf ember. They're the tortoises of the stellar world, slow, steady, and enduring, which makes them intriguing candidates for hosting planets with stable long-term conditions for life to develop. But here's where the story of K2-18b takes a turn into the truly extraordinary when the James Webb Space Telescope turned its golden mirrors toward this distant world. It didn't just confirm what astronomers expected to see, it revealed something that has sent ripples of excitement and bewilderment through the scientific community. The telescope detected something in the planet's atmosphere that shouldn't be there according to our standard models of planetary formation and evolution, a molecule that on Earth is intimately connected with life itself. The molecule in question is dimethyl sulfide, or DOMS, a compound that on our planet is produced almost exclusively by living organisms, particularly marine phytoplankton. Those microscopic floating gardens that drift through our oceans, absorbing sunlight and carbon dioxide and releasing oxygen in return. When these tiny organisms break down, they release DMs into the atmosphere, where it plays a role in cloud formation and climate regulation. It's a molecule so closely tied to biological processes that finding it in the atmosphere of an exoplanet would be like discovering a cosmic signature of life, a chemical calling card that whispers across the light years we are here. Now, before we let our imaginations run wild with visions of alien oceans teeming with extraterrestrial plankton, we must pause and consider the alternatives, because good science requires us to explore every possibility, no matter how mundane, when compared to the tantalizing prospect of discovering life beyond Earth. There are potentially non-biological ways that DOMS could form in an alien atmosphere. Geological processes involving sulfur-bearing rocks, volcanic outgassing, chemical reactions in the upper atmosphere driven by stellar radiation. The universe, it turns out, is quite creative when it comes to chemistry. But even accounting for these possibilities, the presence of DMs in K2-18b's atmosphere remains deeply intriguing, because the conditions on this planet, the temperature, the pressure, the chemical composition, all seem to align in ways that could support not just the existence of liquid water, but potentially the complex chemistry that life requires. It's as if the universe has handed us a cosmic puzzle with pieces that almost but not quite fit together in ways we recognize. The James Webb Space Telescope itself is a marvel that deserves a moment of appreciation. This is not just another telescope. It's humanity's most ambitious attempt to peer deeper into space and further back in time than ever before. Its primary mirror stretches 6.5 meters across, composed of 18 hexagonal segments coated in a microscopically thin layer of gold that gives the telescope its distinctive honeyed appearance. This mirror is so large and so precisely crafted that if it were scaled up to the size of the United States, the largest imperfection would be no bigger than a small hill positioned at a gravitationally stable point called L2, about 1.5 million kilometers from Earth. The James Webb Telescope orbits the Sun in perfect synchronization with our planet, always keeping Earth between itself and the Sun's blinding light. From this cosmic vantage point, it can observe the universe in infrared light wavelengths, longer than what our eyes can see, but perfect for studying the heat signatures of distant worlds and the stretched light from the most ancient galaxies. When we look at K2-18b through Webb's instruments, we're not seeing visible light reflecting off clouds or continents. Instead, we're analyzing the infrared fingerprints left by molecules in the planet's atmosphere as starlight filters through that alien air. The technique is called transmission spectroscopy, and it works on a principle that's almost poetic in its simplicity when K2-18b passes in front of its star. From our perspective, it creates a tiny eclipse, blocking a fraction of the star's light, but not all wavelengths are blocked equally. Some are absorbed by molecules in the planet's atmosphere, creating a unique pattern of absorption lines, like a cosmic barcode that tells us what chemicals are present in that distant world. It's a technique so sensitive that astronomers can detect the presence of water, vapor carbon dioxide, methane, and yes, potentially even dimethyl sulfide in atmospheres hundreds of trillions of kilometers away. The detection of water vapor in K2-18b's atmosphere was itself a significant discovery because it confirmed what astronomers had hoped: a planet in the habitable zone actually has water in its atmosphere. But the potential presence of DMs elevates this discovery to an entirely different level because, if confirmed, it would represent the first detection of a molecule associated with biological processes in the atmosphere of an exoplanet. It would be humanity's first chemical glimpse of what might be life beyond our solar systems. Yet, even as excitement builds in the astronomical community, the scientists involved in this discovery remain refreshingly cautious. They speak in measured tones about the need for additional observations, more data, independent confirmation. They remind us that extraordinary claims require extraordinary evidence, and that the history of astronomy is littered with discoveries that seemed revolutionary until more careful analysis revealed more mundane explanations. It's a healthy skepticism born from centuries of scientific practice. The understanding that the universe is under no obligation to conform to our hopes or expectations. The cautious optimism surrounding K2-18b's reflects something deeper about the nature of scientific discovery. We live in an age where our instruments have become so sophisticated that they can detect the chemical composition of worlds we will never visit, analyze the atmospheres of planets whose surfaces we will never see, and potentially identify signs of life in places so distant that the light carrying that information is older than human civilization. Yet, with this incredible capability comes the responsibility to interpret our findings carefully to distinguish between what we hope to see and what the data actually tells us. K2-18b represents more than just another exoplanet discovery. It embodies humanity's age old quest to answer one of the most profound questions we can ask. Are we alone in the universe for thousands of years? Humans have looked up at the night sky and wondered if somewhere among those points of light there might be other worlds, other forms of life, other intelligences gazing back at us across the cosmic dark. The discovery of K2-18b and the tantalizing hints it offers brings us closer than ever to potentially answering that question. But even as we contemplate the possibility of life on this distant world, we must remember that K2-18b exists in a cosmic context that challenges our Earth-centric assumptions about habitability. Red dwarf stars like K2-18 are prone to violent flares that can strip away planetary atmospheres. They emit most of their energy in infrared wavelengths rather than the visible light that powers photosynthesis on Earth. Planets in the habitable zones of red dwarfs are likely tidally locked with one side always facing the star and the other locked in eternal darkness. These are not Earth-like conditions by any stretch of the imagination. Yet life, if it exists, might find ways to thrive in environments we can barely comprehend. The story of how we came to peer into K2-18b's atmosphere reads like a detective novel written by the universe itself. Each clue carefully hidden in wavelengths of light, each revelation building upon decades of scientific groundwork and technological innovation. The James Webb Space Telescope didn't stumble upon this discovery by accident. It represents the culmination of humanity's most ambitious engineering project, a machine so precise and sensitive that it can taste the chemical breath of worlds circling other stars. When astronomers first pointed Webb's instruments toward K2-18b, they expected to find water vapor, perhaps some carbon dioxide, maybe methane, the usual suspects in the atmospheric lineup of sub-Neptune planets. These are molecules we've learned to recognize the familiar signatures that tell us about temperature, pressure, and basic chemistry. But the data that streamed back from Webb's detectors contained something unexpected, a spectral line that didn't quite match the standard atmospheric models, a whisper of something different hiding in the infrared fingerprints of that distant world. The process of identifying this anomalous signal required months of careful analysis. Teams of scientists poring over data, cross-referencing databases of molecular signatures, running computer models to test different scenarios. Could this unusual absorption line be caused by clouds at a specific altitude, perhaps some unknown photochemical reaction driven by the star's radiation? Or could it be something far more extraordinary? The gradual realization that they might be looking at dimethyl sulfide sent ripples of excitement and skepticism through the research community in equal measure. Dimethyl sulfide on Earth tells a story of biological activity in our oceans. Tiny marine organisms called phytoplankton drift through the sunlit surface waters, conducting photosynthesis. Much like plants on land, when these microscopic creatures die and decompose, they release DMs into the water, which then evaporates into the atmosphere on our planet. This molecule serves as a kind of biological thermostat, helping to regulate cloud formation and climate. It's so intimately connected with life processes that atmospheric scientists use DMs, concentrations, as a proxy for ocean productivity, a chemical signature of the living sea. But K2-18b is not Earth, and the presence of DMs there, if confirmed, would raise profound questions about the nature of life itself. Could there be organisms in that distant world's atmosphere, metabolizing in ways we've never imagined, perhaps floating in dense cloud layers, like the aerial plankton some scientists have proposed might exist in the upper atmosphere of Venus? Or could there be vast oceans beneath thick atmospheric layers teeming with alien microorganisms that produce DMs through biochemical pathways evolution has never explored on Earth? The very idea challenges our terrestrial chauvinism, the tendency to assume that life elsewhere must resemble life here on Earth. We know only one example of biology, our own. Yet the universe contains billions of galaxies each, with billions of stars, many surrounded by planets where chemistry and physics create conditions we can barely comprehend. Ku-18b, with its dense atmosphere and strong gravity, might harbor forms of life that exist in states of matter. We've never encountered organisms that thrive in pressure regimes that would crush earthly creatures like tin cans. The red dwarf star that K2-18b orbits adds another layer of complexity to this cosmic puzzle. Red dwarfs burn their nuclear fuel so slowly and steadily that they can maintain stable energy output for trillions of years, providing potentially stable conditions for life to emerge and evolve over timescales that dwarf the age of complex life on Earth. Yet these stars are also known for their temperamental nature, prone to sudden violent flares that blast their planets with high energy radiation. These stellar tantrums could strip away atmospheric gases, or conversely, they might drive complex chemistry in planetary atmospheres, creating conditions where unusual molecules like DMs could form through purely geological processes. The challenge facing astronomers now is one of patience and precision. Confirming the presence of DMs in Ku-18b's atmosphere requires additional observations, more data points, independent verification from other telescopes. The James Webb Space Telescope, powerful as it is, represents just one set of eyes looking at this distant world. The scientific process demands that extraordinary claims be supported by extraordinary evidence, and the potential detection of a biosignature molecule certainly qualifies as extraordinary. Meanwhile, other research teams are racing to understand what the presence of DMs might actually mean for the possibility of life on K2-18b. Computer models are being refined to explore whether non-biological processes could produce this molecule in the specific conditions expected on a sub-Neptune planet. Laboratory experiments are being designed to test how DMs might behave under different atmospheric pressures and temperatures. The theoretical biologists are wondering what kinds of organisms might thrive in the dense atmosphere of a world 8 times more massive than Earth. The implications extend far beyond K2-18b itself, if dimethyl sulfide can indeed serve as a reliable biosignature, a chemical flag that signals the presence of life. Then astronomers have a new tool in their search for life among the stars. The James Webb Space Telescope and future instruments could begin systematically surveying other potentially habitable exoplanets, looking for this molecular signature of biological activity. It would represent a revolution in astrobiology, transforming the search for life from philosophical speculation to observational science. Yet, even as excitement builds around these possibilities, the story of K2-18b serves as a reminder of how much we still don't know about planets beyond our solar system. The sub Neptune class of planets to which K2-18b belongs has no analog in our own solar system. We have rocky planets like Earth and Mars, gas giants like Jupiter and Saturn, ice giants like Uranus and Neptune, but nothing quite like these intermediate worlds that appear to be among the most common types of planets in the galaxy. Understanding K2-18b requires us to think beyond the familiar categories of planetary science. This world might have a rocky core surrounded by a thick envelope of water and hydrogen, or it could be more like a scaled up version of Earth with a dense atmosphere that creates crushing surface pressures. The boundary between atmosphere and surface might be gradual rather than distinct, a transition zone where gases slowly compress into liquids and then solids as you descend toward the planetary core. The potential presence of DMs adds another variable to this already complex equation. If life exists on K2-18b, it might be unlike anything in our terrestrial experience. Organisms adapted to high pressure environments, dense atmospheres, and the peculiar light of a red dwarf star, they might photosynthesize using infrared radiation, process nutrients through chemistry that would be toxic to earthly life, or exist in symbiotic relationships with atmospheric chemistry that we're only beginning to understand. The red dwarf K2-18 itself presents a fascinating stellar environment for potential life. These stars are so different from our Sun that planets in their habitable zones experience conditions that would be alien to any earthly organism. The star's peak emission occurs in the infrared spectrum rather than visible light, which means any photosynthetic organisms would need to harvest energy from wavelengths our eyes cannot see. The planet is likely tidally locked with one hemisphere, always facing the star, and the other locked in permanent darkness, creating extreme temperature gradients that could drive powerful atmospheric circulation patterns. On the day side of K2, HBB, temperatures might be warm enough for liquid water, while the night side could be cold enough to freeze carbon dioxide. These extreme conditions could create weather patterns unlike anything on Earth, with massive storm systems transferring heat from the illuminated hemisphere to the dark side. The boundary region between day and night, the terminator zone, might offer the most stable conditions for life. A perpetual twilight where temperatures remain moderate and complex chemistry could flourish. The story of K2-18b also highlights the incredible sensitivity of modern astronomical instruments. The potential detection of dimethyl sulfide required measuring absorption lines that represent changes in starlight intensity of less than 1 part in 10,000. It's like detecting the shadow of a gnat passing in front of a lighthouse from a distance of several kilometers. The fact that we can make such measurements at all speaks to the extraordinary precision of the James Webb Space Telescope and the sophisticated techniques astronomers have developed for analyzing exoplanet atmospheres. As we await confirmation of these tantalizing results, the discovery of K2-18b serves as a bridge between the known and unknown, a stepping stone toward answering questions that have fascinated humanity since we first looked up at the stars. Whether or not this distant world harbors life, it has already expanded our understanding of planetary science, atmospheric chemistry, and the incredible diversity of worlds that populate our galaxy. It reminds us that the universe is far stranger and more wonderful than our earthbound imaginations might suggest. The gentle irony is that as we peer deeper into space, searching for signs of life among the stars, we're also discovering just how special and improbable our own existence might be. Earth sits in a delicate balance of conditions that allow liquid water to exist, complex chemistry to flourish, and life to thrive for billions of years. The more we learn about other worlds, the more we appreciate the cosmic lottery that created the conditions for our own existence. Yet K2-18b offers hope that perhaps we are not alone, that somewhere in the vast darkness between stars, other forms of life have found ways to emerge and persist in environments we can barely imagine. The detection methods being used to study K2-18b represent a triumph of human ingenuity, yet they also reveal the profound limitations of our cosmic perspective. When we speak of seeing this distant world, we're not truly seeing it in any conventional sense. No photograph exists of KL2-18b's surface. No image captures its alien skies or possible oceans. Instead, we're reading a story written in starlight, deciphering messages encoded in wavelengths of radiation that have traveled across the void for over a century. The process begins when K2-18b passes between its star and Earth, creating what astronomers call a transit. During these brief alignments, the planet blocks a tiny fraction of its star's light, causing an almost imperceptible dimming that sophisticated instruments can detect. But the real magic happens in the spectrum of that starlight as it filters through the planet's atmosphere. Different molecules absorb different wavelengths, creating a unique fingerprint that tells us about the chemical composition of that distant air. It's a technique so subtle that it borders on the miraculous. Imagine trying to determine what someone had for dinner by analyzing the way candlelight filters through their breath from across a crowded stadium. The precision required is staggering, yet astronomers have refined these methods to the point where they can detect trace amounts of molecules in atmospheres hundreds of trillions of kilometers away. The potential presence of dimethyl sulfide in K2-18b's atmosphere represents just one piece of a much larger puzzle. Webb has also detected water vapor, carbon dioxide, and possibly methane, creating a complex chemical portrait of this alien world. Each molecule tells part of the story about temperature, pressure, and the dynamic processes shaping that distant atmosphere. Together, they paint a picture of a world that's both familiar and utterly foreign. Water vapor, in particular, serves as a crucial piece of evidence for the planet's potential habitability. On Earth, atmospheric water vapor is constantly cycling between liquid and gas phases, evaporating from oceans and lakes, condensing into clouds, and falling as precipitation. The presence of water vapor in K2-18b's atmosphere suggests similar processes might be occurring there, perhaps indicating vast bodies of liquid water beneath the dense atmospheric layers. Carbon dioxide adds another dimension to our understanding of this world's climate system. On Earth, CO2 acts as a greenhouse gas, trapping heat and helping to maintain temperatures suitable for liquid water. The amount of carbon dioxide in K2-18b's atmosphere could determine whether the planet's surface is pleasantly warm or scorchingly hot, whether any liquid water remains stable or boils away into the vacuum of space. Methane presents perhaps the most intriguing possibility of all. On Earth, methane is produced both by geological processes and by living organisms, particularly microbes that thrive in oxygen poor environments. The detection of methane in K2-18b's atmosphere could indicate active geology, with volcanic processes releasing gases from the planet's interior. Or it could suggest something far more exciting: biological processes producing this simple hydrocarbon as a waste product of alien metabolism. The interplay between these different molecules creates a complex atmospheric chemistry that scientists are still working to understand. Computer models attempt to simulate the conditions on K2E18b, testing different scenarios for how these gases might interact under the planet's specific conditions of temperature, pressure, and stellar radiation. Some models suggest the atmosphere might be stable and conducive to liquid water at the surface. Others indicate a more turbulent environment, where powerful greenhouse effects could create crushing surface pressures and temperatures hot enough to melt lead. The red dwarf star K2-18 adds its own complications to these atmospheric models. Red dwarfs are known for their violent outbursts, sudden flares that can temporarily increase their brightness by factors of 10 or more. These stellar tantrums blast nearby planets with intense ultraviolet and X ray radiation, potentially stripping away atmospheric gases or driving complex photochemical reactions that could create unusual molecular signatures. Yet red dwarfs also offer unique advantages for the development of life. Their incredible longevity means that planets orbiting these stars have vast amounts of time for life to emerge and evolve. While our sun will burn for about 10 billion years, red dwarfs can maintain stable nuclear fusion for hundreds of billions or even trillions of years. If life did emerge on K2-18b, it would have virtually unlimited time to diversify and adapt to changing conditions. The tidal lock-in of planets around red dwarfs creates another fascinating aspect of K2-18b's environment. With one hemisphere permanently facing the star and the other locked in eternal darkness, the planet likely experiences extreme temperature gradients that drive powerful atmospheric circulation patterns. Massive storm systems might constantly transfer heat from the day side to the night side, creating dynamic weather patterns unlike anything we experience on Earth. These circulation patterns could actually help stabilize the planet's climate, preventing the day side from becoming too hot and the night side from freezing solid. The terminator zone, the boundary region between day and night, might offer particularly stable conditions where temperatures remain moderate and complex chemistry could flourish in the eternal twilight. The density and composition of K2-18b's atmosphere remain subjects of intense scientific debate. Some models suggest the planet might have a hydrogen rich atmosphere inherited from its formation, similar to the gas giants in our own solar system, but compressed to much higher densities by the planet's stronger gravity. Other models propose a steam atmosphere dominated by water vapor, created when the planet's surface oceans were heated and vaporized by stellar radiation. The truth might lie somewhere between these extremes, with K2-18b possessing a complex layered atmosphere where different chemical processes dominate at different altitudes. Near the surface, liquid water might exist under high pressure, while higher in the atmosphere, complex organic molecules could form through photochemical reactions driven by the star's radiation. The potential detection of dimethyl sulfide adds a biological dimension to these atmospheric models. On Earth, DMS is primarily produced by marine microorganisms, particularly phytoplankton that drift through the sunlit surface waters of our oceans. These tiny organisms form the base of marine food webs, converting sunlight and carbon dioxide into organic matter through photosynthesis. When they die and decompose, they release DMS as a byproduct, which then evaporates into the atmosphere. If similar processes occur on K2-18b, they would require liquid water environments where microorganisms could thrive. The planet's strong gravity and dense atmosphere might create conditions where liquid water exists over a wide range of temperatures and pressures, potentially supporting forms of life adapted to extreme conditions. Those hypothetical organisms might be unlike anything on Earth, perhaps existing as floating colonies in dense atmospheric layers or thriving in high pressure environments that would be instantly lethal to terrestrial life. The search for biosignatures, like dimethyl sulfide, represents a new frontier in astronomy, transforming the ancient question of whether we are alone in the universe from philosophical speculation into observational science. For the first time in human history, we have instruments capable of detecting chemical evidence of life on worlds orbiting other stars. The implications are staggering. If confirmed, the presence of DMS in K2-18b's atmosphere would represent humanity's first chemical glimpse of extraterrestrial life. Yet the scientists involved in this research remain admirably cautious, emphasizing the need for additional observations and independent confirmation. The history of astronomy is filled with discoveries that seemed revolutionary until more careful analysis revealed more mundane explanations. The detection of apparent biosignatures requires extraordinary evidence precisely because the implications are so profound. The James Webb Space Telescope will continue to observe K-SART-18b, gathering more data to confirm or refute the initial findings. Other telescopes will join the effort, providing independent measurements that can verify the presence of these intriguing molecules. The process will likely take months or even years, as scientists carefully analyze each piece of evidence and test alternative explanations for the observed spectral signatures. Meanwhile, the discovery of K2-18b is already inspiring new research directions and technological developments. Astronomers are identifying other potentially habitable sub-Neptune planets that could be studied with similar techniques. Engineers are designing even more sensitive instruments that could detect fainter biosignatures and characterize exoplanet atmospheres in greater detail. Theoretical biologists are exploring what forms of life might be possible under the extreme conditions found on these alien worlds. The story of K2-18b also highlights the remarkable progress in exoplanet science over the past few decades. When the first planet orbiting another star was discovered in 1995, it seemed almost miraculous that we could detect such distant worlds at all. Today, we know of thousands of exoplanets, and we're beginning to characterize their atmospheres, measure their temperatures, and search for signs of habitability or even life itself. This rapid progress reflects not just advances in technology, but also the development of new theoretical frameworks for understanding planetary systems. We've learned that planets like those in our solar system represent just a small fraction of the possible worlds that can form around other stars. The galaxy is populated by super Earths, hot Jupiters, mini Neptunes, and other exotic planet types that have no analogs in our own cosmic neighborhood. K218b belongs to this category of alien worlds that challenges our Earth centric assumptions about planetary science. Its intermediate size between Earth and Neptune, its dense atmosphere, and its orbit around a red dwarf star create conditions that we can barely comprehend based on our terrestrial experience. Yet it's precisely these alien conditions that make the planet so intriguing as a potential abode for life. The gentle paradox is that as we search for life among the stars, we're discovering that Earth itself might be far more unusual than we ever imagined. The specific combination of factors that allowed complex life to emerge and thrive on our planet, from our planet's size and orbital distance to the stability of our sun and the presence of our large moon, might be relatively rare in the galaxy. Yet K218b suggests that life, if it exists, might find ways to emerge under conditions we would consider utterly hostile. As we drift deeper into contemplation of these distant worlds, there's something both humbling and inspiring about the realization that we live in an age when such discoveries are possible. For most of human history, other worlds remained purely in the realm of imagination and speculation. Today, we can analyze the chemical composition of atmospheres light years away and search for signs of life among the stars. We stand at the threshold of potentially answering one of the most profound questions we can ask. Are we alone in the universe? The quest to understand K218b forces us to confront the limitations of our cosmic vocabulary. We describe this world as a sub-Neptune because we lack better terms, but what does that really mean in the context of a universe filled with planetary architectures we've never encountered? Imagine trying to describe the color blue to someone who has never seen the sky, or explain the sensation of floating to someone who has never left solid ground. We find ourselves in a similar predicament when attempting to characterize worlds that exist in the spaces between our familiar categories. The atmospheric pressure on K218b might be dozens of times greater than what we experience on Earth, creating conditions where the boundary between liquid and gas becomes beautifully blurred. Water might exist in states we rarely encounter on our planet, perhaps as a supercritical fluid that flows like liquid but fills space like gas. These are not merely academic distinctions. They represent fundamentally different environments where the chemistry of life, if it exists at all, might unfold according to rules we're only beginning to glimpse. Consider the profound strangeness of photosynthesis under a red dwarf star on Earth. Plants and algae have evolved to harvest the energy of our sun's bright yellow light, converting carbon dioxide and water into organic compounds that fuel the biosphere, but K218 emits most of its energy in the infrared spectrum wavelengths that feel like heat rather than light to our human senses. Any photosynthetic organisms on K218b would need to capture and convert this invisible radiation into biological energy, creating biochemical pathways that have no equivalent on Earth. The tidal locking of K218b creates another layer of environmental complexity that challenges our terrestrial assumptions about habitability. Imagine a world where half the sky never changes, where the star hangs motionless at one point in the heavens, while the other hemisphere experiences eternal night. Between these extremes lies the terminator zone, a band of perpetual twilight, where temperatures might remain stable enough for complex chemistry to flourish. In this twilight realm, Atmospheric circulation patterns could create a kind of global weather system unlike anything we observe on Earth. Hot air rising from the day side might carry moisture and heat toward the night side, where it cools and condenses before flowing back as part of a planet wide circulation pattern. These massive atmospheric rivers could distribute energy and chemical compounds across the globe, creating niches where life might find purchase in the most unexpected places. The detection techniques used to study K2-18b represent humanity's most sophisticated attempt to eavesdrop on distant worlds. Yet they also reveal how much we still don't understand about the cosmos. The light that carries information about this planet's atmosphere left K2-18 sometime around the year 1900, when our understanding of physics, chemistry, and biology was far more primitive than it is today. The photons now reaching the James Webb Telescope have been traveling through space longer than powered flight has existed on Earth. This temporal displacement creates a strange kind of cosmic archaeology. We're studying the past of a world we'll never visit, analyzing the chemical composition of an atmosphere as it existed when our great grandparents were children. Any changes that might have occurred on K2-18b since then remain invisible to us, hidden behind the fundamental speed limit of the universe, the speed of light itself. The implications extend far beyond mere technical curiosity. If life exists on K18b, and if that life has been evolving for billions of years, then we might be glimpsing just the faintest shadow of what could be an entire biosphere teeming with organisms. We cannot imagine the dimethyl sulfide potentially detected in the planet's atmosphere might represent the collective breath of countless microorganisms, each one a unique solution to the problem of existing in an alien environment. Yet we must also consider the possibility that we're seeing something else entirely. Perhaps K2-18b produces dimethyl sulfide through geological processes. We don't yet understand volcanic outgassing driven by the planet's internal heat might release sulfur compounds that react with other atmospheric gases to create DEAMs through purely chemical pathways. The universe, after all, has a talent for creating complexity through non biological processes. The debate over whether K2-18b harbors life touches on deeper questions about the nature of biology itself. We know only one example of life, our own terrestrial biosphere, with its DNA-based organisms, its dependence on liquid water, its specific temperature and pressure requirements. But life, as we don't know it, might operate according to entirely different principles, using alternative biochemistries that could thrive in environments we consider utterly hostile. Some scientists speculate about organisms that might exist in the dense atmospheres of sub-Neptune planets, floating colonies of microbes that never touch solid ground, but instead drift through layers of gas and vapor, extracting energy from chemical gradients or stellar radiation. These aerial ecosystems might be more common than surface-based life in the galaxy, simply because dense atmospheres can exist over a wider range of conditions than liquid oceans. The red dwarf K2-18 itself presents both challenges and opportunities for the development of life. Stellar flares could strip away atmospheric gases or create harmful radiation environments, but they might also drive atmospheric chemistry in ways that promote the formation of complex organic molecules. The same violent stellar activity that seems hostile to life might actually be essential for creating the chemical diversity necessary for biology to emerge. The longevity of red dwarf stars creates another fascinating dimension to consider. While our sun will eventually expand into a red giant and then fade to a white dwarf ember, K2-18 will continue burning steadily for trillions of years. If life did emerge on K2-18b, it would have virtually unlimited time to evolve and diversify into forms we cannot possibly anticipate. The search for biosignatures like dimethyl sulfide represents more than just a technical achievement. It embodies humanity's deepest aspirations to understand our place in the cosmic order. For thousands of years, we have wondered whether the Earth represents a unique oasis of life, or whether biology is a common feature of planetary systems throughout the galaxy. The potential detection of DMs on K2-18b brings us tantalizingly close to answering this ancient question. But even if K2-18b proves to be lifeless, the planet has already taught us valuable lessons about the incredible diversity of worlds that populate our galaxy. It has shown us that habitable zones around other stars might harbor conditions utterly unlike those on Earth, yet still potentially suitable for life, as we don't know it. The planet serves as a bridge between the familiar and the alien, a stepping stone toward understanding planetary systems that operate according to different rules. The James Webb Space Telescope continues to gather data about K2-18b, each observation adding new details to our understanding of this distant world. Additional transits will provide more precise measurements of atmospheric composition, while longer observations might reveal seasonal changes or other temporal variations in the planet's atmospheric chemistry. The patient accumulation of data represents the slow, methodical process by which science transforms speculation into knowledge. Meanwhile, other sub-Neptune planets are being identified and characterized, creating a growing catalog of worlds that might harbor conditions suitable for life. The techniques developed to study K28 taps are being refined and applied to other potentially habitable exoplanets, expanding our search for biosignatures beyond a single intriguing world. Each new detection adds another piece to the cosmic puzzle we're trying to solve. The story of K2-18b also highlights the collaborative nature of modern astronomy. The potential detection of dimethyl sulfide in the planet's atmosphere required not just the extraordinary sensitivity of the James Webb Space Telescope, but also the combined expertise of atmospheric chemists, planetary scientists, astrobiologists, and data analysts working together to interpret complex spectroscopic measurements. This collaborative approach reflects a deeper truth about the search for life beyond Earth. It requires input from multiple scientific disciplines, each contributing unique perspectives and methodologies. The question of whether we are alone in the universe cannot be answered by astronomy alone, but requires insights from biology, chemistry, geology, and even philosophy. As we grapple with what it means to be alive in a cosmos that might be teeming with alternative forms of existence. The potential presence of life on K2-18b would also raise profound questions about the frequency and distribution of biology in the galaxy. If life can emerge on a sub-Neptune planet orbiting a red dwarf star, then it might be far more common than we ever dared hope. The galaxy contains billions of red dwarfs, many with planets in their habitable zones, creating countless opportunities for life to emerge and evolve, Conversely, if K218b proves to be lifeless despite its apparently favorable conditions, it might suggest that the emergence of life requires an even more specific set of circumstances than we currently understand. The absence of life on such a promising world would be a significant data point in our efforts to understand the factors that allow biology to emerge from chemistry. As we contemplate these possibilities, there's something both thrilling and sobering about our cosmic perspective. We live in an age when we can analyze the atmospheres of worlds orbiting other stars, yet we remain fundamentally limited by the speed of light and the vast distances between stars. We can glimpse the chemical signatures of distant worlds, but we will likely never visit them, never sample their airs directly, never walk upon their surfaces. This limitation creates a unique form of cosmic longing, a desire to know more about worlds we can study but never truly explore. Q218b exists in a realm that is simultaneously accessible to our instruments and forever beyond our physical reach. We can taste its atmospheric chemistry through spectroscopy, but we will never breathe its air, never feel the pull of its stronger gravity, never witness firsthand whether life has found a way to thrive in its alien environment. The gentle irony is that as we search for life among the stars, we're also discovering just how special and improbable our own existence might be. Earth occupies a narrow zone of conditions that allow liquid water to exist, complex chemistry to flourish, and life to diversify over billions of years. The more we learn about other worlds, the more we appreciate the cosmic lottery that created the conditions for our own biosphere. Yet K218b offers hope that perhaps we are not alone, that somewhere in the vast darkness between stars, other forms of life have found ways to emerge and persist in environments we can barely imagine, whether that life produces dimethyl sulfide in dense atmospheric layers or thrives through biochemistries. We haven't yet conceived remains to be seen, but the very possibility transforms our understanding of what it means to be alive in this universe. The detection of potential biosignatures on K218b also raises important questions about how we should respond to the discovery of life beyond Earth. The protocols for announcing such a discovery remain a subject of ongoing debate among scientists and policymakers. The confirmation of extraterrestrial life would represent one of the most significant discoveries in human history, requiring careful communication and thoughtful consideration of the implications. As we await further observations and analysis of K218b, the planet serves as a powerful reminder of how far we've come in our understanding of the cosmos and how much we still have to learn. The universe continues to surprise us with its creativity and complexity, revealing worlds that challenge our assumptions and expand our conception of what is possible. The story of K218b is far from over. Additional observations will either confirm or refute the presence of dimethyl sulfide in its atmosphere, but regardless of the outcome, this distant world has already expanded our understanding of planetary science, atmospheric chemistry, and the incredible diversity of environments where life might potentially emerge. In the quiet moments between observations, as astronomers around the world wait for new data from the James Webb Space Telescope, K218b continues its ancient orbit around its red dwarf star, carrying whatever secrets it might hold through the cosmic dark. Whether those secrets include life, remains one of the most tantalizing questions in science, a question that may soon find its answer in the whispered messages of starlight filtered through an alien atmosphere. As we drift deeper into the mystery of K218b, there's something almost dreamlike about the way this discovery unfolds. Like a story told in whispers across cosmic distances, each piece of evidence arrives not as a dramatic revelation, but as a gentle nudge toward understanding something profound about the nature of worlds beyond our own. The dimethyl sulfide signal, if it truly exists, represents more than just a molecular detection. It embodies humanity's first potential glimpse into the biochemical processes of an alien world, a chemical conversation carried on stellar winds across 124 light years of empty space. Yet the very faintness of this signal reminds us how delicate our cosmic eavesdropping really is. We're attempting to detect the equivalent of a whisper in a hurricane, a single molecule's signature buried within the complex symphony of an entire planetary atmosphere. The challenges of confirming this detection highlight the beautiful complexity of modern astronomy. Each observation with the James Webb Telescope requires precise timing, waiting for K218b to align perfectly between its star and Earth. These transit events occur roughly every 33 days, but atmospheric conditions, telescope scheduling, and the delicate dance of orbital mechanics mean that each opportunity is precious. Scientists must wait patiently for these cosmic alignments, much like photographers waiting for the perfect light to capture an elusive scene. The data itself arrives as a stream of numbers, wavelengths, and intensity measurements that must be carefully calibrated and analyzed. Teams of researchers spend months poring over these digital breadcrumbs, searching for patterns that might reveal the chemical secrets of this distant world. It's meticulous work, requiring both technical expertise and the kind of patient dedication that drives the best scientific discoveries. Meanwhile, the theoretical implications of K218b continue to ripple through various fields of science. Atmospheric modelers are working to understand how dimethyl sulfide might behave in the high pressure environment of a sub-Neptune planet. The molecule that on Earth exists primarily in dilute concentrations in our relatively thin atmosphere might behave very differently under conditions where atmospheric pressure could be dozens of times greater than what we experience. These modeling efforts reveal just how much we're still learning about atmospheric chemistry under extreme conditions. Oh, laboratory experiments on Earth can only approximate the environment of K2-18b, and computer simulations must make assumptions about chemical reaction rates and molecular behavior in regimes we've never directly studied. It's a bit like trying to predict how a recipe might taste when prepared in a kitchen with completely different temperature, pressure, and ingredient availability. The biological implications, should the dimethyl sulfide detection be confirmed, stretch our understanding of life itself. On Earth, the organisms that produce DMS have evolved over billions of years to thrive in our planet's specific conditions. They use familiar biochemical pathways, operate within comfortable temperature ranges, and exist in environments where liquid water is readily available. But life on K2-18b, if it exists, would need to operate under fundamentally different rules. Imagine microorganisms adapted to atmospheric pressures that would instantly crush terrestrial life, or biochemical processes that operate efficiently in the infrared rich light of a red dwarf star. These hypothetical organisms might exist in states between liquid and gas, perhaps as part of vast atmospheric ecosystems that have no equivalent on Earth. They might process nutrients through chemical pathways that would be toxic to earthly life, or exist in symbiotic relationships with atmospheric chemistry that creates a kind of planet wide metabolism. The possibility of aerial life forms floating in K2-18b's dense atmosphere particularly captures the imagination of astrobiologists. Unlike Earth, where most life exists on solid surfaces or in liquid oceans, a sub-Neptune planet might support entire ecosystems suspended in layers of gas and vapor. These floating communities could extract energy from chemical gradients, stellar radiation, or atmospheric electrical activity, creating food webs that exist entirely in three-dimensional space. Such aerial ecosystems might actually be more common in the galaxy than the surface-based biospheres we're familiar with. Dense atmospheres can exist over a wider range of planetary conditions than stable liquid oceans, and they might provide more consistent, long term environments for life to evolve. The upper atmospheres of gas giants in our own solar system have been proposed as potential habitats for floating microorganisms, though we lack the technology to directly test these intriguing hypotheses. The red dwarf K2-18 continues to add layers of complexity to our understanding of this system. Recent observations have revealed more details about the star's magnetic field and stellar activity patterns, information that's crucial for understanding how the star's radiation might affect its planet's atmosphere and potential biology. Red dwarfs can maintain stable energy output for trillions of years, but they're also prone to sudden flares that release intense bursts of radiation. These stellar outbursts might seem hostile to life, but they could also play important roles in driving atmospheric chemistry and evolution. The high energy radiation from stellar flares can break apart molecules in planetary atmospheres, creating reactive chemical species that might not form under quieter conditions. This radiation driven chemistry could contribute to the production of complex organic compounds, or it might help maintain chemical disequilibrium states that could support biological processes. The tidal locking of K2-18b creates another fascinating aspect of this world's environment that we're only beginning to understand. The permanent day-night division means that atmospheric circulation patterns play a crucial role in distributing heat and chemical compounds around the planet. Computer models suggest that massive jet streams might carry material from the hot day side to the cold night side, creating a global weather system unlike anything we observe in our solar system. Those circulation patterns could create distinct atmospheric layers with different chemical compositions and physical conditions. The day side might be dominated by high temperature chemistry driven by direct stellar radiation, while the night side could host cooler processes that allow complex molecules to condense and accumulate. The terminator zone between day and night might offer the most stable conditions, where temperatures and chemical environments remain relatively constant over long periods. Understanding these atmospheric dynamics is crucial for interpreting the spectroscopic data we receive from K2-18b. The molecules we detect represented a global average of the planet's atmospheric composition, but the actual distribution of these compounds might vary dramatically with location and altitude. The dimethyl sulfide signal, if confirmed, might originate from specific regions or atmospheric layers where conditions are particularly favorable for its production. The international collaboration required to study K2-18b reflects the global nature of modern astronomy. Teams from different countries and institutions contribute specialized expertise in spectroscopy, atmospheric modeling, theoretical biology, and data analysis. This collaborative approach not only improves the quality of the research, but also ensures that multiple independent groups can verify and validate the findings. The peer review process for such extraordinary claims is particularly rigorous. Before any announcement of a potential biosignature detection, the research must be scrutinized by experts in multiple fields, each bringing their own perspective and skepticism to bear on the evidence. This process can take months or even years, but it helps ensure that when scientific conclusions are announced, they represent the best current understanding of the available data. Meanwhile, other potentially habitable exoplanets are being identified and studied using similar techniques. Each new world adds to our growing understanding of planetary atmospheres and the conditions that might support life. Some planets show clear signs of water vapor but lack other interesting molecules. Others display complex atmospheric chemistry but orbit in conditions that might be too extreme for biology as we understand it. This comparative approach to exoplanet studies is helping astronomers develop a more nuanced understanding of habitability. Rather than simply looking for Earth like conditions, researchers are beginning to recognize that life might emerge under a much broader range of circumstances than we initially assumed. The concept of the habitable zone around stars is expanding to include considerations of atmospheric composition, planetary mass, and stellar activity that weren't part of earlier models. The study of K2-18b is also pushing the boundaries of what's technically possible with current instruments. The James Webb Telescope represents the pinnacle of current technology, but even its extraordinary sensitivity is stretched to its limits when attempting to detect trace molecules in exoplanet atmospheres. Future telescopes, currently in the planning and development stages, will have even greater capabilities for this kind of research. These next generation instruments will be able to study smaller, more Earth like planets and detect even fainter atmospheric signatures. They might also be capable of directly imaging some exoplanets, providing visual information to complement the spectroscopic data we currently rely on. The combination of these different observational approaches will give us unprecedented insights into the nature of worlds orbiting other stars. As we await further observations of K2-18b, the planet continues to orbit its red dwarf star in the constellation Leo, carrying whatever secrets it might hold through the cosmic darkness. Whether those secrets include life remains one of the most tantalizing questions in modern science. The gentle whispers of starlight filtering through its atmosphere may eventually tell us whether we are alone in the universe or whether life has found ways to flourish in environments we can barely imagine. The story of K2-18b reminds us that the universe is under no obligation to conform to our expectations or desires. It may harbor life in forms we've never conceived, or it might be utterly barren despite appearing promising from our distant perspective. Either outcome would be scientifically valuable, adding to our understanding of how planets form, how atmospheres evolve, and what conditions are necessary for biology to emerge from chemistry. There's something profoundly humbling about the realization that we live in an age when such questions can be addressed through observation rather than mere speculation. For most of human history, the possibility of life on other worlds remained purely in the realm of philosophy and imagination. Today, we can analyze the chemical composition of atmospheres light years away and search for molecular evidence of biological processes among the stars. The gentle irony is that as our instruments become more sophisticated and our techniques more refined, we're discovering that the universe is even stranger and more complex than our wildest dreams had suggested. Every new exoplanet discovery challenges our assumptions about planetary formation and evolution. Every atmospheric analysis reveals chemical processes we hadn't anticipated. Every potential biosignature detection forces us to reconsider what we think we know about the nature and distribution of life in the cosmos. K2-18b sits at the center of these expanding possibilities, a world that bridges the gap between the familiar and the utterly alien. Its sub-Neptune classification places it in a category of planets that has no analog in our solar system, yet its location in the habitable zone suggests conditions that might, just might, be suitable for life. The potential presence of dimethyl sulfide in its atmosphere adds another layer of mystery to this already intriguing world. As telescopes around the world continue to gather data about this distant planet, teams of scientists work quietly to unravel the meaning of each spectral line and atmospheric signature. The process is methodical, sometimes tedious, but driven by the understanding that they might be on the verge of one of the most significant discoveries in human history. The confirmation of life beyond Earth would fundamentally change our understanding of our place in the universe and our relationship to the cosmos that gave us birth. Whether K2-18b will provide that confirmation remains to be seen. The planet might prove to be a tantalizing false alarm, its atmospheric chemistry explainable through purely geological processes. Or it might harbor forms of life so different from terrestrial biology that we struggle to recognize them as alive at all. Either way, this distant world has already expanded our conception of what's possible in the universe, reminding us that reality often surpasses the boundaries of our imagination. In the quiet hours when astronomers around the world pause to contemplate the implications of their work, Ki-2-18b serves as a powerful symbol of humanity's endless curiosity about the cosmos. This small, distant world represents both the limits of our current knowledge and the boundless potential for discovery that lies ahead. As we drift towards sleep beneath our own familiar stars, somewhere in the constellation Leo, K2-18b continues its ancient dance around its red dwarf sun, holding its secrets close, waiting for the next transit, the next observation, the next gentle whisper of starlight that might finally tell us whether we are alone. The quest to understand K2-18b has become something of a cosmic detective story, where each clue arrives encoded in wavelengths of light that have traveled farther than human civilization has existed. The scientists studying this distant world must piece together evidence from the faintest of signals, building theories from shadows and whispers carried on stellar winds. What makes this investigation particularly challenging is the sheer complexity of atmospheric chemistry under conditions we've never directly encountered. The dense atmosphere of K2-18b likely experiences pressures and temperatures that exist nowhere on Earth, creating chemical environments where familiar molecules might behave in completely unfamiliar ways. It's rather like trying to predict how a symphony might sound when performed by instruments you've never heard in a concert hall built from materials that don't exist. The potential presence of dimethyl sulfide becomes even more intriguing when considered within this context of extreme atmospheric conditions. On Earth, this molecule exists primarily in our relatively thin atmosphere, where it plays its role in biological cycles under pressures we consider normal. But in the crushing depths of K2-18b's atmospheric layers, DMS might participate in chemical reactions that have no terrestrial equivalent, or it might be produced through pathways that evolution has never explored on our world. Recent computer models attempting to simulate K2-18b's atmospheric chemistry have revealed just how much we still don't understand about molecular behavior under such extreme conditions. The models must account for pressures dozens of times greater than Earth's surface pressure, temperatures that fluctuate dramatically between day and night sides, and radiation environments shaped by a red dwarf star's peculiar energy output. Each variable introduces uncertainties that compound as the simulations attempt to predict the complex dance of atmospheric chemistry. The James Webb Telescope's continued observations are gradually filling in these gaps in our understanding, but each new piece of data seems to raise as many questions as it answers. Recent measurements have revealed subtle variations in the planet's atmospheric composition that might indicate seasonal changes, or perhaps long-term chemical cycles that operate on timescales we're only beginning to appreciate. These temporal variations add another layer of complexity to an already intricate puzzle. The search for additional biosignature molecules in K2-18b's atmosphere has become a priority for several research teams around the world. While dimethyl sulfide represents the most tantalizing potential detection, scientists are also looking for other compounds that might indicate biological processes. Phosphine, for instance, has been proposed as another potential biosignature, though its detection would be even more challenging given the current limitations of our instruments. The concept of biosignatures themselves continues to evolve as we learn more about the incredible diversity of planetary environments in the galaxy. What constitutes evidence of life depends heavily on the specific conditions of each world, and molecules that might be clear indicators of biology on one planet could be produced through purely geological processes on another. This contextual nature of biosignature interpretation makes the study of K2-18b's both more complex and more fascinating. The red dwarf K2-18 continues to surprise astronomers with its behavior patterns. Recent observations have revealed that the star's magnetic field is more dynamic than initially thought, creating complex interactions with any planetary magnetic fields in the system. These magnetic interactions could influence atmospheric chemistry on K2-18b in ways we're only beginning to understand, potentially creating or destroying molecules through processes that have no equivalent in our solar system. The tidal forces exerted by K2-18 on its planet create another source of energy that might drive unusual chemistry. The constant gravitational stress could generate internal heating through tidal flexing, similar to what we observe on Jupiter's moon Io, though on a much larger scale. This internal energy source might power geological processes that release gases into the atmosphere, or it could create temperature gradients that drive complex circulation patterns. Understanding the role of tidal heating in K2-18b's evolution requires sophisticated models that account for the planet's internal structure, composition, and thermal history. These models suggest that the planet might have experienced significant atmospheric evolution over its lifetime, with periods of intense outgassing followed by more stable phases. The current atmospheric composition we observe might represent just one snapshot in a long history of chemical change. The possibility of subsurface oceans on K2 to 18b adds another dimension to our consideration of this world's potential habitability. Even if the planet's surface conditions prove too extreme for life as we know it, liquid water might exist beneath the dense atmospheric layers, protected from the harsh radiation environment of the red dwarf star. These hidden oceans could provide stable environments where biology might flourish, occasionally releasing telltale molecules into the atmosphere above. The detection techniques being refined for K2-18b studies are pushing the boundaries of what's possible with current technology. Astronomers are developing new methods for extracting weak signals from noisy data, using machine learning algorithms to identify subtle patterns that might escape human analysis. These computational approaches are becoming increasingly important as we attempt to study ever more distant and challenging targets. The international collaboration surrounding K2-18b research has grown into one of the largest cooperative efforts in modern astronomy. Teams from dozens of institutions across multiple continents contribute specialized expertise, from atmospheric modeling and laboratory spectroscopy to theoretical biology and data analysis. This collaborative approach not only improves the quality of the research, but also helps ensure that multiple independent groups can verify and validate any extraordinary claims. The peer review process for K2-18b research has become particularly rigorous, given the potential implications of confirming a biosignature detection. Manuscripts undergo scrutiny from experts in atmospheric chemistry, planetary science, astrobiology, and observational astronomy. This multidisciplinary review process can take many months, but it helps ensure that any announced discoveries represent the best current understanding of the available evidence. Meanwhile, the search for similar worlds continues with increasing sophistication. Astronomers have identified dozens of other sub-Neptune planets in the habitable zones of red dwarf stars, creating a growing sample for comparative studies. Each new world adds to our understanding of how these intermediate-sized planets form and evolve, and what conditions might be necessary for them to maintain atmospheres capable of supporting life. The diversity of atmospheric compositions among these sub-Neptune worlds is already challenging our assumptions about planetary formation. Some show clear evidence of hydrogen-rich atmospheres inherited from their formation process, while others appear to have undergone significant atmospheric evolution that has altered their chemical signatures. K2-18b sits somewhere in this spectrum with atmospheric properties that suggest a complex evolutionary history. Recent theoretical work has explored how life might actually function in the dense atmospheric environments of sub-Neptune planets. These studies suggest that aerial ecosystems might be not just possible, but potentially more stable than surface based biospheres. Floating communities of microorganisms could extract energy from atmospheric chemistry, stellar radiation, or electrical phenomena, creating food webs that exist entirely in three-dimensional space. The concept of atmospheric life forms has particular relevance for K2-18b, where surface conditions might be too extreme for terrestrial style biology. If life exists on this world, it might take the form of vast microbial communities suspended in the planet's dense atmosphere, processing nutrients through biochemical pathways we've never encountered on Earth. These organisms might exist in layers where temperature and pressure conditions remain stable, creating distinct ecological zones at different altitudes. The energy sources available for potential life on K2-18b are quite different from those that power Earth's biosphere. The red dwarf star emits most of its energy in infrared wavelengths rather than visible light, which would require any photosynthetic organisms to harvest energy from radiation we experience as heat rather than light. This fundamental difference could lead to biochemical processes that operate according to entirely different principles than terrestrial photosynthesis. Chemical energy sources might be equally important for potential K2-18b organisms. The planet's dense atmosphere and possible geological activity could create chemical gradients that organisms might exploit for energy, much like certain bacteria on Earth derive energy from chemical reactions rather than sunlight. The extreme conditions might actually provide more diverse energy sources than are available on Earth, potentially supporting more complex ecosystems than we might initially expect. The temporal aspects of K2-18b research add another layer of complexity to our understanding. The light we observe from this system left the planet more than a century ago, meaning we're studying the atmospheric composition as it existed in the early 1900s by Earth's calendar. Any changes that might have occurred since then remain hidden from our view, creating a fundamental limitation in our ability to understand the planet's current state. This temporal displacement becomes particularly relevant when considering potential biological processes. If life exists on K2-18b and has been evolving for billions of years, the organisms present today might be significantly different from those that produce the atmospheric signatures we're currently detecting. Evolution doesn't pause while light travels across interstellar distances, and any biosphere on K2-18b would continue developing even as we analyze century old evidence of its existence. The philosophical implications of K2-18b research extend far beyond the technical challenges of atmospheric analysis. The potential discovery of life on this distant world would force us to reconsider fundamental questions about the nature of biology, the distribution of life in the universe, and our own place in the cosmic order. It would represent humanity's first confirmed detection of life beyond our solar system, a discovery that would rank among the most significant in human history. Yet even if K2-18b proves to harbor no life at all, the planet has already expanded our understanding of planetary science and atmospheric chemistry in ways we couldn't have anticipated. It has shown us that the universe creates worlds under conditions we can barely comprehend, and that the search for life must consider environments far stranger than our Earth based experience might suggest. The gentle irony of K2-18b research is that as we develop more sophisticated techniques for studying distant worlds, we're discovering that the universe is even more creative and complex than we had imagined. Every new exoplanet discovery reveals unexpected atmospheric compositions, unusual orbital characteristics, or planetary properties that challenge our theoretical models. The cosmos seems determined to surprise us with its endless capacity for creating environments we've never conceived. As winter evenings grow longer and the constellation Leo climbs higher in our nighttime sky, K2-18b continues its ancient orbit around its red dwarf companion, carrying whatever secrets it might hold through the cosmic darkness. The planet remains tantalizingly beyond our physical reach, yet increasingly accessible to our instruments and our imagination. Whether those secrets include the chemical signatures of life remains one of the most compelling questions in modern science. The story of K2-18b is still being written, one observation at a time, one spectral analysis at a time, one carefully peer-reviewed paper at a time. The process is methodical and sometimes frustratingly slow, but it represents humanity's most ambitious attempt to answer questions that have fascinated us since we first looked up at the stars and wondered if we might not be alone. In the quiet hours between observations, as telescopes around the world pause and recalibrate, K2-18b continues its cosmic dance, holding its atmospheric secrets close, while light from its red dwarf star begins another century-long journey toward Earth. That light, when it finally reaches us, will carry information about the planet's current state, adding new chapters to a story that began with whispers of an unusual molecular signature in the infrared spectrum of a distant world. The search for life beyond Earth has become one of the defining scientific endeavors of our time, and K2-18b sits at the heart of that quest. Whether this sub-Neptune world will provide the answer we're seeking remains to be seen, but its very existence reminds us that the universe is vast, strange, and full of possibilities we're only beginning to explore. As we settle deeper into the contemplation of this distant world, there's something quietly profound about the realization that K2-18b represents more than just another entry in our growing catalog of exoplanets. It embodies a fundamental shift in how we approach the search for life beyond Earth, moving from hopeful speculation to methodical investigation of actual chemical evidence carried across the void on beams of ancient starlight. The atmosphere of K2-18b, if we could somehow experience it directly, would likely be unlike anything a human has ever encountered. Imagine air so dense that breathing it would be impossible, not just because of its composition, but because the very pressure would compress your lungs beyond function. Yet within this crushing envelope of gas and vapor, chemistry unfolds according to rules that stretch the boundaries of what we consider possible. Recent atmospheric models suggest that the planet might exist in a state of perpetual chemical flux, with molecules constantly forming and breaking apart under the influence of stellar radiation, gravitational heating, and the strange physics of high-pressure environments. The dimethyl sulfide signal, should it prove real, might represent just one note in a vast atmospheric symphony of chemical processes that we're only beginning to hear. The red dwarf K2-18 continues to reveal new aspects of its character as astronomers study it more closely. Unlike our Sun, which burns with relatively steady output, red dwarfs can be temperamental neighbors, prone to sudden outbursts that flood nearby space with radiation. These stellar tantrums might seem hostile to life, but they could also serve as cosmic chemistry sets, breaking apart simple molecules and providing the energy needed to forge more complex compounds. The interplay between stellar activity and planetary atmospheric chemistry creates feedback loops that we're still learning to understand. A particularly violent flare might strip away portions of K2-18b's atmosphere, but it could also drive chemical reactions that produce new molecules or maintain existing ones that would otherwise break down over time. It's a delicate balance between destruction and creation, played out on scales that dwarf anything we observe in terrestrial chemistry. The tidal locking of K2-18b adds yet another layer of complexity to this already intricate system. The permanent division between day and night sides creates temperature gradients steep enough to drive massive atmospheric circulation patterns. These global weather systems might transport chemical compounds across vast distances, creating distinct atmospheric zones where different types of chemistry dominate. On the perpetually illuminated day side, intense stellar radiation might drive high energy chemical reactions that break apart complex molecules and create reactive species that exist nowhere on Earth. The eternal night side, by contrast, might serve as a kind of atmospheric freezer where molecules can condense and accumulate in concentrations impossible under the harsh radiation of direct starlight. The terminator zone, that eternal twilight region between day and night, might offer the most stable conditions for complex chemistry to unfold. Here, temperatures remain relatively constant, and the interplay between hot and cold atmospheric masses could create chemical gradients that organisms might exploit for energy, much like certain bacteria on Earth derive sustenance from chemical differences in their environment. The concept of life in such an environment challenges every assumption we make about biology based on our terrestrial experience. Any organisms that might exist on KO2-18b would need to be adapted not just to different atmospheric composition, but to pressure regimes that would instantly destroy earthly life, radiation environments that would sterilize terrestrial organisms, and energy sources that have no equivalent on our planet. Yet the more we learn about life on Earth, the more we discover that biology is remarkably adaptable to extreme conditions. Deep sea organisms thrive under crushing pressure near hydrothermal vents. Extremophile bacteria flourish in environments so acidic, hot, or radioactive that they were once thought to be completely sterile. These discoveries suggest that life, once it emerges, might be far more resilient and creative than we ever imagined. The potential for aerial life forms in K2-18b's dense atmosphere particularly captures the imagination of researchers studying this distant world. Unlike Earth, where most life exists either on solid surfaces or in liquid oceans, a sub-Neptune planet might support entire ecosystems suspended in layers of gas and vapor. These floating communities could exist at altitudes where temperature and pressure conditions remain stable, creating three-dimensional habitats unlike anything in our terrestrial experience. Such atmospheric organisms might extract energy from chemical gradients in the planet's layered atmosphere, or perhaps from the electrical phenomena that could arise from the interaction between charged particles and the planet's magnetic field. They might exist as vast colonial organisms, like aerial coral reefs, or as microscopic individuals that form complex ecological networks spanning entire atmospheric layers. The chemistry required to support such life would likely be unlike anything we observe on Earth. These hypothetical organisms might metabolize compounds that are toxic to terrestrial life, or they might exist in biochemical states that blur the line between liquid and gas. They could operate at temperatures and pressures that would denature the proteins essential to earthly biology, using alternative biochemistries that evolution has never explored in our more temperate environment. The detection of dimethyl sulfide, if confirmed, would provide the first chemical evidence that such exotic life forms might actually exist. But even this detection raises more questions than it answers. Would the DMS be produced by organisms similar to Earth's marine phytoplankton, or by entirely different forms of life that happen to excrete this particular molecule as a waste product? Could the chemical signature we're detecting represent the collective metabolism of countless microscopic organisms, or the byproduct of some exotic atmospheric chemistry we haven't yet imagined? The patient work of confirming this detection continues in laboratories and observatories around the world. Each new observation with the James Webb Telescope adds another data point to the growing dataset, while atmospheric chemists work to understand how dimethyl sulfide might behave in the extreme conditions of K2-18b's atmosphere. The process is methodical, sometimes tedious, but driven by the understanding that they might be gathering evidence of the most significant discovery in human history. Meanwhile, the search for other potential biosignatures in K2-18b's atmosphere continues with increasing sophistication. Research teams are looking for patterns in the data that might indicate seasonal changes in atmospheric composition, or perhaps long term variations that could suggest biological cycles operating on timescales we're only beginning to appreciate. Each subtle change in the planet's spectroscopic signature might hold clues about the dynamic processes shaping this distant world. The international collaboration studying K2-18b has grown into one of the most comprehensive research efforts in modern astronomy. Scientists from dozens of institutions contribute specialized expertise, sharing data and insights across traditional boundaries of nationality and institutional affiliation. This cooperative approach not only improves the quality of the research, but also helps ensure that any extraordinary claims are thoroughly vetted by multiple independent teams. The peer review process for K2-18b research reflects the extraordinary nature of the potential discovery. Manuscripts undergo scrutiny from experts in atmospheric chemistry, planetary formation, astrobiology, and observational techniques. The review process can take many months, with reviewers requesting additional analysis, alternative explanations, and independent confirmation of key findings. It's a rigorous process designed to ensure that any announced discoveries represent the best current understanding of the available evidence. The broader implications of K2-18b research extend far beyond the specific question of whether this particular world harbors life. The techniques being developed to study this planet's atmosphere are being applied to dozens of other potentially habitable exoplanets, creating a systematic survey of atmospheric compositions across a wide range of planetary types and stellar environments. This comparative approach is revealing that planetary atmospheres are far more diverse and dynamic than we ever anticipated. Some worlds show clear evidence of atmospheric escape, with their gases slowly bleeding away into space. Others appear to have undergone dramatic atmospheric evolution, transforming from one type of world into something completely different over geological timescales. K2-18b sits within this spectrum of atmospheric diversity, offering insights into how intermediate sized planets evolve and maintain their gaseous envelopes. The study of sub-Neptune atmospheres, like K2-18b's, is also informing our understanding of planetary formation processes. These worlds appear to be among the most common types of planets in the galaxy, yet they have no equivalent in our own solar system. Understanding how they form, what determines their atmospheric composition, and what conditions allow them to maintain stable environments over billions of years is crucial for predicting where life might emerge among the stars. Recent theoretical work has explored the potential for atmospheric phase transitions on worlds like K2-18b, where the boundary between gas and liquid might be gradual but rather than distinct. These supercritical fluid environments could provide unique habitats where organisms might exist in states that have no terrestrial equivalent. The chemistry of such environments remains largely unexplored, offering vast territories for both theoretical investigation and potential biological innovation. The energy budget of K2-18b presents another fascinating aspect of this world's potential habitability. The planet receives energy not just from stellar radiation, but potentially from tidal heating caused by gravitational interactions with its star. This internal energy source could drive geological processes that release gases into the atmosphere or create temperature gradients that support complex circulation patterns and chemical cycling. The magnetic field of K2-18b, if it exists, would play a crucial role in shaping the planet's atmospheric environment. A strong magnetic field could protect the atmosphere from erosion by stellar wind and high energy radiation, while also creating charged particle interactions that might drive exotic chemistry. The absence of a magnetic field, conversely, could lead to atmospheric loss over time, but might also allow for direct interaction between stellar radiation and atmospheric gases that could promote the formation of complex organic molecules. The temporal evolution of K2-18b's atmosphere adds another dimension of complexity to our understanding of this distant world. The atmospheric composition we observe today represents the cumulative result of billions of years of chemical evolution, stellar activity, and potentially biological processes. Unraveling this history requires sophisticated models that account for changing stellar output, atmospheric escape, and the complex feedback loops between geology, chemistry, and potential biology. The search for temporal variations in K2-18b's atmospheric composition has become a priority for several research teams. Subtle changes in molecular concentrations over time could indicate seasonal cycles driven by the planet's orbital motion, or perhaps longer-term variations related to stellar activity or atmospheric circulation patterns. These temporal signatures might also provide evidence of biological processes that operate on cycles different from those we observe on Earth. The philosophical implications of K2-18b research continue to resonate through scientific and cultural communities around the world. The potential discovery of life beyond Earth would fundamentally alter humanity's understanding of its place in the universe, transforming us from a unique cosmic accident into part of a broader biological community that spans the stars. Even the failure to find life on such a promising world would provide valuable insights into the rarity and preciousness of biological processes. The gentle irony of our search for life on K218b is that it forces us to confront the limitations of our terrestrial perspective while simultaneously expanding our conception of what might be possible in the universe. We approach this alien world with instruments and theories developed through our experience on Earth. Yet we must remain open to the possibility that life elsewhere might operate according to principles we've never encountered. As autumn deepens and the constellation Leo rises earlier each night, K218b continues its ancient orbit around its red dwarf companion, carrying whatever secrets it might hold through the cosmic darkness. The planet remains physically beyond our reach, yet it has already begun to reshape our understanding of planetary science, atmospheric chemistry, and the potential for life to emerge under conditions far different from those that gave rise to our own biosphere. The story of K218b represents humanity's first serious attempt to chemically eavesdrop on a potentially life-bearing world beyond our solar system. Whether that eavesdropping will reveal the whispered secrets of alien biology or simply teach us more about the exotic chemistry possible in dense planetary atmospheres remains to be seen. Either outcome would represent a profound addition to our understanding of the universe and our place within it. In the quiet moments between observations, as telescopes around the world pause to recalibrate and researchers analyze the latest data, K218b continues its cosmic dance, holding its atmospheric secrets close, while starlight from its red dwarf sun begins another century-long journey toward Earth. That future light, when it finally reaches our instruments, will carry information about the planet's evolving state, adding new chapters to a story that began with the faint, spectroscopic whispers of molecules suspended in an alien sky. The search for life beyond Earth has become one of the defining quests of our technological age, and K218b sits at the heart of that endeavor. This distant world reminds us that the universe is vast, strange, and filled with possibilities we're only beginning to explore. Whether it will provide the answer to our deepest question about cosmic loneliness remains unwritten, but its very existence suggests that the universe may be far more alive and dynamic than we ever dared hope. The search for answers about Ku-218b has taken on an almost meditative quality, requiring the kind of patient observation that astronomers have practiced for centuries, yet applied to questions that would have seemed like pure fantasy just decades ago. Each night that the James Webb Telescope turns its golden eye toward this distant world, we're essentially asking the universe to reveal one of its most closely guarded secrets, whether the spark of life has ignited in places far removed from our familiar Earth. The molecular detective work continues with an almost archaeological precision. Scientists sift through spectroscopic data, much like researchers might examine layers of ancient sediment, looking for telltale chemical signatures that speak to processes occurring in environments we can never directly experience. The dimethyl sulfide signal, if it truly exists, represents not just a molecular detection, but a potential conversation starter with forms of life that might think, breathe, and exist according to rules we've never imagined. Recent advances in atmospheric modeling have revealed just how dynamic K2-18b's chemical environment might be. Unlike Earth's relatively stable atmosphere, this distant world likely experiences constant chemical churning driven by the peculiar physics of dense gaseous environments. Molecules that might survive for years in our thin atmosphere could be created and destroyed within hours in the crushing depths of K2-18b's atmospheric layers, creating a kind of chemical weather system operating on timescales we're only beginning to appreciate. The red dwarf K2-18 continues to surprise researchers with its complex behavior patterns. Recent observations have revealed magnetic field fluctuations that could create auroral displays in K2-18b's atmosphere if anyone were there to witness them. These magnetic interactions might also drive atmospheric chemistry in ways that have no equivalent in our solar system, potentially creating or destroying molecules through processes that exist nowhere else in our cosmic neighborhood. The possibility of subsurface processes on K2-18b adds another layer of intrigue to this already complex world. Deep beneath the dense atmospheric layers, geological activity driven by tidal heating might create conditions where different types of chemistry could flourish. These hidden processes could occasionally release gases into the atmosphere above, creating chemical signatures that we might detect from our distant vantage point without ever understanding their true origin. The concept of life existing in such an environment continues to stretch our biological imaginations. Any organisms that might call K2-18b home would need to be fundamentally different from terrestrial life, adapted to pressures that would crush earthly creatures and radiation environments that would sterilize most known biological processes. Yet the very extremity of these conditions might provide opportunities for biochemical innovation that evolution has never explored on our more temperate world. The atmospheric layers of K2-18b might support distinct ecological zones, each with its own chemical environment and potential biological inhabitants. High altitude regions might host organisms adapted to intense stellar radiation, while deeper atmospheric layers could harbor life forms that thrive in the crushing pressure and chemical richness of the planet's lower atmosphere. Between these extremes, countless intermediate zones might provide niches for biological communities we can barely conceive. The energy sources available for potential life on K2-18b differ fundamentally from those that power Earth's biosphere. The infrared-rich radiation from the red dwarf star would require photosynthetic organisms to harvest energy from wavelengths that feel like heat rather than light to our human senses. Chemical energy sources might be equally important, with the planet's dense atmosphere providing chemical gradients that organisms could exploit, much like certain bacteria on Earth derive energy from chemical differences in their environment. The temporal aspects of studying K2-18b continue to add philosophical depth to this scientific investigation. We're analyzing atmospheric conditions as they existed more than a century ago, studying a world frozen in the cosmic amber of light travel time. Any biological evolution that might be occurring on K2-18b continues even as we examine evidence of its past, creating a fundamental disconnect between what we can observe and what might currently exist on this distant world. The collaborative nature of K2-18b research has grown into something resembling a global scientific community united by shared curiosity about this enigmatic world. Researchers from different continents and cultural backgrounds contribute their expertise to understanding atmospheric chemistry, planetary formation, and the potential for life under extreme conditions. This international cooperation reflects the universal human desire to understand our place in the cosmos and whether we might share it with other forms of consciousness. The technological challenges of studying K2-18b continue to push the boundaries of what's possible with current instruments. The James Webb Telescope operates at the very limits of its sensitivity when analyzing the faint atmospheric signatures of this distant world, requiring hundreds of hours of observation time to gather enough data for meaningful analysis. Future telescopes will undoubtedly improve upon these capabilities, but for now, we work with whispers and shadows, building theories from the faintest of cosmic signals. The peer review process for K2-18b research has become particularly thorough, reflecting the extraordinary nature of the potential discoveries involved. Multiple independent teams verify each finding, testing alternative explanations, and searching for systematic errors that might lead to false conclusions. This methodical approach ensures that any announced discoveries represent genuine advances in our understanding rather than wishful thinking or instrumental artifacts. The broader implications of K2-18b research extend far beyond the specific question of life on this particular world. The techniques being developed to study its atmosphere are being applied to dozens of other potentially habitable exoplanets, creating a systematic survey of atmospheric compositions that reveals the incredible diversity of planetary environments in our galaxy. Each new world studied adds to our understanding of how planets form, evolve, and potentially support life. The study of sub-Neptune atmospheres like K2-18b's is revealing that these intermediate-sized worlds might be among the most common types of planets in the galaxy, yet they represent environments completely unknown in our own solar system. Understanding how they maintain their dense atmospheric envelopes over billions of years and what chemical processes shape their evolution is crucial for predicting where life might emerge among the countless worlds orbiting other stars. Recent theoretical investigations have explored the possibility of phase transitions in K2 to 18b's atmosphere, where the boundaries between gas, liquid, and solid states become blurred under extreme pressure and temperature conditions. These supercritical environments might provide unique habitats where organisms could exist in states of matter that have no terrestrial equivalent, opening entirely new possibilities for biological innovation. The magnetic environment around K2's 8 types, while still poorly understood, could play a crucial role in shaping the planet's atmospheric chemistry and potential habitability. Interactions between the planet's magnetic field, if it exists, and the charged particle environment of its red dwarf star could create conditions that either protect potential life from harmful radiation or drive exotic chemistry through electromagnetic processes we've never observed in our own solar system. The atmospheric circulation patterns on Ku-218b likely create a kind of global chemistry laboratory where different regions of the planet experience vastly different chemical conditions. The perpetual day side might be dominated by high-energy photochemistry driven by direct stellar radiation, while the eternal night side could host slower, more complex chemical processes that benefit from cooler temperatures and protection from harmful radiation. The terminator zone between day and night sides might offer the most stable conditions for complex chemistry or even biology to flourish. In this region of eternal twilight, temperatures could remain relatively constant, while atmospheric circulation brings together chemical compounds from both the hot and cold hemispheres, creating unique reaction conditions that exist nowhere else on the planet. The search for temporal variations in K2-18b's atmospheric composition has become increasingly sophisticated, with researchers looking for subtle changes that might indicate seasonal cycles, long term climate evolution, or even biological processes operating on timescales different from those we observe on Earth. These temporal signatures, if detected, could provide crucial insights into the dynamic processes shaping this distant world. The energy budget of K2U18b includes not just stellar radiation, but potentially significant internal heating from tidal forces exerted by its red dwarf star. This gravitational heating could drive geological processes that release gases into the atmosphere, maintain liquid water reservoirs beneath the surface, or create temperature gradients that support complex atmospheric circulation patterns. Understanding these energy sources is crucial for predicting whether the planet could maintain stable conditions suitable for life over geological timescales. The chemical inventory of K2-18b's atmosphere continues to grow more complex as observation techniques improve and analysis methods become more sophisticated. Beyond the headline grabbing potential detection of dimethyl sulfide, researchers are identifying numerous other molecular species that paint a picture of a world undergoing constant chemical transformation. Each new molecular detection adds another piece to the puzzle of how this alien world operates. The possibility of cloud formation in K2-18b's dense atmosphere adds yet another layer of complexity to our understanding of this world's climate system. Clouds on this planet might be composed of materials that would seem exotic from our terrestrial perspective, perhaps condensed metal vapors or organic compounds that exist as solids only under the extreme conditions found in the planet's upper atmosphere. These alien weather systems could dramatically affect the planet's energy balance and atmospheric chemistry. The concept of atmospheric life forms has gained increasing attention as researchers grapple with the realities of K2-18b's environment. If life exists on this world, it might take the form of vast aerial ecosystems suspended in the planet's dense atmosphere, extracting energy from chemical gradients, electromagnetic phenomena, or the complex interplay between different atmospheric layers. Such life would represent a completely novel form of biological organization, unlike anything we observe on Earth. The red dwarf stellar environment presents both challenges and opportunities for potential life on K2 to 18b. While the star's tendency toward violent flares might seem hostile to biological processes, these energetic events could also drive atmospheric chemistry that creates or maintains complex organic molecules. The long term stability of red dwarf stars might provide the extended timescales necessary for life to emerge and evolve in environments very different from those that supported the development of Earth's biosphere. The philosophical implications of K2-18b research continue to resonate through scientific and cultural communities worldwide, The potential discovery of life on this distant world would represent humanity's first confirmed detection of biology beyond our solar system, fundamentally altering our understanding of life's prevalence and diversity in the universe. Even negative results would provide valuable constraints on the conditions necessary for life to emerge and thrive. The gentle irony of our investigation of K218b is that the more we learn about this distant world, the more we appreciate both the universality and the uniqueness of the conditions that allowed life to flourish on Earth. Our planet's specific combination of size, composition, orbital characteristics, and stellar environment might be relatively rare in the galaxy, yet the existence of worlds like K1 and 18b suggests that life might find ways to emerge under conditions we consider utterly alien. The story of K218b serves as a powerful reminder that the universe is under no obligation to conform to our terrestrial expectations about how worlds should behave or what conditions might support life. This distant planet challenges our assumptions while simultaneously expanding our conception of what might be possible in the vast cosmos that surrounds us. As winter approaches and the constellation Leo becomes more prominent in our evening sky, K218b continues its ancient orbital dance around its red dwarf companion, carrying whatever secrets it might hold through the cosmic darkness. The planet remains physically beyond our reach, yet it has already begun to transform our understanding of planetary science and the potential for life to emerge under conditions far different from those we call home. The patient work of understanding K28b continues in observatories and laboratories around the world, driven by the recognition that we might be gathering evidence of one of the most significant discoveries in human history. Whether this distant world will ultimately reveal signs of life or simply teach us more about the exotic chemistry possible in alien atmospheres, it has already earned its place as one of the most important worlds in our growing catalog of exoplanets. In the quiet hours between observations, as telescopes pause and data flows through fiber optic cables toward research institutions around the globe, K218b holds its secrets close while continuing its cosmic journey through space and time. The whispers of starlight that carry information about this distant world remind us that we live in an age of unprecedented discovery, when the ancient human dream of understanding our place in the universe has become a matter of careful observation and patient analysis rather than mere speculation and hope. The investigation of K218b has become something of a cosmic meditation on the nature of discovery itself. Here we are, creatures bound to a single world, peering across impossible distances to decipher the chemical breath of an alien planet. It's rather like trying to understand a symphony by feeling the vibrations through the concert hall floor, yet somehow, remarkably, we're beginning to make sense of the music. The dimethyl sulfide detection, should it prove genuine, represents far more than a simple molecular identification. It would be our first chemical handshake with processes occurring in an environment so alien that we lack adequate words to describe it. The molecule itself becomes a kind of cosmic messenger, carrying information about conditions, chemistry, and perhaps even biology across 124 years of interstellar travel. Recent computational models have revealed just how extraordinary the atmospheric dynamics of K218b might be. The planet's dense gaseous envelope likely experiences pressure waves and chemical cascades that operate on scales dwarfing anything we observe in Earth's relatively gentle atmosphere. Imagine storm systems where the very chemistry of the air changes as weather patterns sweep across continents of gas, where molecular species form and dissipate like clouds in an alien sky. The red dwarf K218 continues to reveal new facets of its character as our observations grow more detailed. These ancient stars burn with a patience that spans geological epochs, yet they can erupt with sudden violence that floods nearby space with radiation. Each stellar outburst might strip away portions of KU-218b's atmosphere while simultaneously driving chemical reactions that create new molecular species in the planet's upper layers. The interplay between stellar activity and atmospheric chemistry creates feedback loops of staggering complexity. A particularly energetic flare might temporarily alter the planet's entire chemical balance, triggering cascading reactions that ripple through different atmospheric layers like chemical avalanches. These events, occurring over timescales ranging from hours to decades, could create the dynamic chemical environment where unusual molecules like dimethyl sulfide might form through processes we're only beginning to imagine. The gravitational dance between K2-18b's and its star adds another dimension to this already intricate system. Tidal forces constantly knead the planet's interior, potentially driving geological processes that release gases into the atmosphere through mechanisms that have no equivalent on Earth. The very shape of the planet might fluctuate subtly as it orbits, creating internal friction that generates heat and drives chemical cycling between the planet's interior and its gaseous envelope. The concept of life in such an environment pushes the boundaries of biological imagination to their limits. Any organisms that might exist on K2-18b would need to be adapted not just to different atmospheric composition, but to a reality where the very medium of existence shifts and changes according to physical laws we barely comprehend. They might exist as vast colonial organisms distributed through multiple atmospheric layers, or as microscopic entities that thrive in the chemical chaos of a world in constant flux. The energy sources available for potential K2-18b biology differ so fundamentally from terrestrial life that we struggle to envision how such organisms might function. The infrared-dominated radiation from the red dwarf star would require photosynthetic processes that harvest energy from wavelengths our eyes cannot see. Chemical energy sources might be equally exotic, with organisms potentially deriving sustenance from pressure gradients, electromagnetic phenomena, or chemical reactions that occur only under extreme atmospheric conditions. The atmospheric layering on K2-18b likely creates distinct ecological zones, each with its own chemical signature and physical characteristics. High-altitude regions might experience conditions similar to the upper reaches of gas giant atmospheres, while deeper layers could resemble the crushing depths of terrestrial oceans, but composed entirely of gas and vapor. Between these extremes, countless intermediate environments might provide niches for biological innovation we cannot currently conceive. The temporal evolution of K2-18b's atmosphere represents a story written in chemical signatures across billions of years. The atmospheric composition we observe today reflects the cumulative influence of stellar evolution, planetary formation, and potentially biological processes operating over timescales that dwarf the entire history of complex life on Earth. Unraveling this chemical archaeology requires models that account for changing stellar output, atmospheric escape, and the complex feedback loops between geology, chemistry, and hypothetical biology. The search for periodic variations in K2-18b's atmospheric chemistry has become increasingly sophisticated as researchers develop new techniques for extracting subtle signals from noisy data. Any detected changes could indicate seasonal cycles driven by the planet's orbital motion, long term climate variations, or even biological processes that operate according to rhythms completely different from those we observe on Earth. The magnetic environment surrounding coating 18s remains one of the most poorly understood aspects of this distant world. If the planet possesses a magnetic field, it could create complex interactions with the charged particle environment of its red dwarf star, potentially driving atmospheric chemistry through electromagnetic processes that exist nowhere in our solar system. Alternatively, the absence of a strong magnetic field might allow direct interaction between stellar radiation and atmospheric gases, creating conditions where exotic chemistry could flourish. The atmospheric circulation patterns on KOA-218b likely operate as a kind of planetary scale chemistry laboratory, with different regions experiencing vastly different chemical conditions depending on their exposure to stellar radiation, atmospheric pressure, and local temperature gradients. The perpetual day side might be dominated by high energy photochemical reactions, while the eternal night side could host more complex, slower chemical processes that benefit from cooler temperatures and protection from harmful radiation. The terminator zone, that eternal twilight region between day and night, might offer the most stable conditions for complex chemistry or even biology to develop. Here, in the perpetual dawn or dusk of this alien world, temperatures could remain relatively moderate, while atmospheric circulation brings together chemical compounds from both hemispheres, creating unique reaction conditions that exist nowhere else on the planet. The detection techniques being used to study K2218b represent humanity's most ambitious attempt to practice chemistry at interstellar distances. Each spectroscopic measurement requires extraordinary precision, detecting changes in starlight that represent variations smaller than the width of a human hair viewed from several kilometers away. The fact that we can make such measurements at all speaks to the remarkable ingenuity of modern astronomical instrumentation and the dedicated work of countless engineers and scientists. The collaborative nature of K2-18b research has created something resembling a global scientific community united by curiosity about this enigmatic world. Researchers from different continents, cultures, and scientific traditions contribute their expertise to understanding atmospheric chemistry under extreme conditions, stellar planetary interactions, and the theoretical foundations of astrobiology. This international cooperation reflects the universal human desire to understand whether we share the cosmos with other forms of life. The peer review process for K2-18b research has evolved to meet the extraordinary nature of potential biosignature detections. Multiple independent research teams verify each finding, testing alternative explanations, and searching for systematic errors that might lead to false conclusions. The process can take months or even years, but it ensures that any announced discoveries represent genuine advances in our understanding rather than instrumental artifacts or wishful thinking. The technological challenges of studying K2-18b continue to drive innovation in astronomical instrumentation and data analysis techniques. Machine learning algorithms are being developed to extract weak signals from complex datasets, while new observational strategies are being designed to maximize the scientific return from precious telescope time. These advances will benefit not just K2-18b research, but the entire field of exoplanet atmospheric characterization. The broader implications of K2-18b research extend far beyond questions about this specific world. The techniques being refined for its study are being applied to dozens of other potentially habitable exoplanets, creating a systematic survey of atmospheric compositions that reveals the incredible diversity of planetary environments in our galaxy. Each new world studied adds to our understanding of planetary formation, atmospheric evolution, and the potential for life to emerge under conditions different from those on Earth. The study of sub-Neptune atmospheres like K2-18b's is revolutionizing our understanding of planetary science. These intermediate-sized worlds appear to be among the most common types of planets in the galaxy, yet they represent environments completely unknown in our own solar system. Understanding how they form, maintain their atmospheric envelopes, and evolve over billions of years is crucial for predicting where life might emerge among the countless worlds orbiting other stars. The concept of atmospheric phase transitions in K2-18b's dense gaseous envelope opens entirely new realms of theoretical investigation. Under extreme pressure and temperature conditions, the boundaries between different states of matter become blurred, creating environments where traditional concepts of solid, liquid, and gas lose their meaning. These supercritical conditions might provide unique habitats where life could exist in forms we cannot currently imagine. The energy budget of K2-18b includes contributions from stellar radiation, tidal heating, and potentially radioactive decay in the planet's interior. This complex energy balance determines whether the planet can maintain stable atmospheric conditions over geological timescales and whether any subsurface liquid reservoirs might exist to support alternative forms of life. Understanding these energy sources requires sophisticated models that account for the planet's internal structure, composition, and thermal history. The chemical inventory of K2-18b's atmosphere continues to grow more detailed as observational techniques improve and theoretical understanding advances. Each newly detected molecular species adds another piece to the puzzle of how this alien world operates, revealing chemical processes that might have no equivalent on Earth. The atmosphere serves as a kind of chemical fingerprint, encoding information about the planet's formation, evolution, and current state. The possibility of exotic cloud systems in K2-18b's atmosphere adds another layer of complexity to our understanding of this world's climate. Clouds composed of condensed metal vapors, organic compounds, or other materials that exist as gases under Earth conditions could dramatically affect the planet's energy balance and atmospheric chemistry. These alien weather systems might create localized chemical environments where unusual reactions could occur. The red dwarf stellar environment presents a unique set of challenges and opportunities for atmospheric chemistry and potential biology. While stellar flares might seem hostile to life, They could also drive complex chemical reactions that create or maintain organic molecules in the planet's atmosphere. The long term stability of red dwarf stars provides the extended timescales that might be necessary for life to emerge and evolve under conditions very different from those that supported Earth's biosphere. The philosophical implications of K2-18b research continue to resonate through scientific and broader cultural communities. The potential discovery of life on this distant world would represent humanity's first confirmed detection of biology beyond our solar system, fundamentally altering our understanding of life's prevalence in the universe. Even if no life is found, the planet teaches us about the incredible diversity of environments that exist among the stars. The gentle paradox of studying K2-18b is that the more we learn about this alien world, the more we appreciate both the commonality and the uniqueness of planetary processes throughout the galaxy. While the specific conditions on Earth might be relatively rare, the existence of worlds like K2-18b suggests that nature finds countless ways to create complex, dynamic environments where chemistry and potentially biology can flourish. The story of K2-18b represents a new chapter in humanity's oldest quest, understanding our place in the cosmic order. This distant world challenges our terrestrial assumptions while simultaneously expanding our conception of what might be possible in the vast universe that surrounds us. Whether it harbors life or simply teaches us about exotic atmospheric chemistry, K2-18b has already earned its place as one of the most scientifically significant worlds beyond our solar system. As the seasons turn and the constellation Leo traces its ancient path across our night sky, K2-18b continues its orbital dance around its red dwarf companion, carrying whatever secrets it might hold through the cosmic darkness. The planet remains forever beyond our physical reach, yet it has already begun to transform our understanding of planets, atmospheres, and the potential for life to emerge under conditions far different from those we call home. The patient work of understanding K2-18b continues in observatories and research institutions around the world, driven by the recognition that we might be witnessing one of the most profound discoveries in human history. Each new observation, each refined analysis, each theoretical insight brings us closer to answering questions that have fascinated our species since we first looked up at the stars and wondered whether we might not be alone. In the quiet hours between observations, as data flows through global networks and researchers collaborate across continents and time zones, K2-18b holds its atmospheric secrets close while continuing its ancient journey through space and time. The whispers of starlight that carry information about this distant world remind us that we live in an extraordinary age, when the dream of understanding our cosmic context has become a matter of patient observation and careful analysis, rather than mere speculation and hope. The search for life beyond Earth has become one of the defining endeavors of our technological civilization, and K2-18b sits at the heart of that quest. This enigmatic world, with its dense atmosphere and tantalizing chemical signatures, represents our best current opportunity to detect the molecular fingerprints of biology among the stars. Whether those fingerprints will ultimately be confirmed remains an open question, but the very possibility has already expanded our understanding of what it means to be alive in this vast, dynamic, an endlessly surprising universe. Tonight, as we prepare to drift away from this distant world and back to the familiar warmth of our own small planet, there's something quietly profound about what K218b has taught us, even as it keeps its deepest secrets locked away in layers of alien air. This sub-Neptune world, suspended in its eternal dance around a red dwarf star, has become more than just another entry in our growing catalog of exoplanets. It represents a bridge between the known and the unknowable, a cosmic stepping stone that has carried us closer to answering one of humanity's most profound questions, while simultaneously revealing just how much we still don't understand about the universe we inhabit. The potential presence of dimethyl sulfide in that distant atmosphere may ultimately prove to be a false alarm, a trick of light and chemistry that has no biological origin, or it might represent our first chemical glimpse of life beyond Earth, a molecular hello whispered across more than a century of space and time. Either way, K218b has already transformed how we think about worlds beyond our solar system and the countless ways that chemistry might unfold under conditions we can barely comprehend. The patient work of confirmation continues, with telescopes around the world gathering photons that have traveled farther than human civilization has existed, encoding their precious cargo of information in wavelengths that speak to instruments sensitive enough to detect the breath of distant worlds. Each observation adds another brushstroke to a portrait we're painting of a place none of us will ever visit, a world that exists in the realm between data and dreams. The red dwarf K218 will continue burning steadily for trillions of years, long after our own sun has expanded and faded, long after the last light has gone out on Earth. If life has indeed found a foothold in that alien atmosphere, it has virtually unlimited time to evolve and diversify into forms we cannot possibly anticipate. The very longevity of red dwarf systems suggests that the universe might be far more patient with the development of life than our own relatively brief stellar timeline might suggest. As we've journeyed through the complexities of this distant world, from its crushing atmospheric pressures to its exotic chemistry, from the peculiar physics of tidal locking to the theoretical possibilities of aerial ecosystems, we've been reminded that the cosmos has a talent for creating environments that stretch our imaginations to their limits. K218b exists in a realm where familiar concepts like weather and climate take on entirely new meanings, where the very air might be alive with processes we've never encountered on our temperate world. The collaboration required to study this distant planet has created something beautiful in its own right, a global community of researchers united by curiosity about a world none of them will ever touch. From atmospheric chemists modeling exotic reactions to theoretical biologists imagining impossible life forms, from engineers pushing the limits of telescope sensitivity to data analysts searching for patterns in cosmic whispers. The investigation of K218b has become a testament to what we can accomplish when we combine human ingenuity with patient observation. The gentle irony of our quest to understand K218b's is that it has taught us as much about ourselves and our own world as it has about distant planets. Each comparison we make between Earth's familiar processes and the alien chemistry of a sub-Neptune atmosphere reminds us of the extraordinary chain of circumstances that allowed our own biosphere to emerge and flourish. We are, it seems, both more common and more precious than we ever imagined. The techniques being developed to study K2-18b's atmosphere will outlive any individual discovery about this particular world. These methods are already being applied to dozens of other potentially habitable exoplanets, creating a systematic survey of atmospheric compositions that reveals the staggering diversity of planetary environments in our galaxy. Each new world studied adds another piece to the cosmic puzzle we're trying to solve, bringing us closer to understanding whether biology is a rare cosmic accident or a common feature of planetary systems throughout the universe. The story of K2-18b also serves as a powerful reminder of how rapidly our understanding of exoplanets has evolved. Just a few decades ago, the very existence of planets around other stars was a matter of speculation rather than observation. Today, we routinely analyze the chemical composition of alien atmospheres and search for molecular signatures that might indicate the presence of life. Tomorrow, we may have instruments capable of directly imaging these distant worlds and studying their surfaces in unprecedented detail. Whether K2-18b ultimately proves to harbor life or remains a fascinating example of exotic atmospheric chemistry, it has already secured its place in the history of human discovery. This distant world has shown us that the universe is capable of creating environments we never anticipated, that chemistry can unfold under conditions that would instantly destroy terrestrial life, and that the search for life among the stars requires us to expand our conception of what biology might look like under alien skies. The patient accumulation of data about K2-18b continues, driven by the understanding that extraordinary claims require extraordinary evidence. The scientific process demands careful verification, independent confirmation, and thorough exploration of alternative explanations. This methodical approach ensures that when discoveries are announced, they represent genuine advances in our understanding rather than wishful thinking or instrumental error. In the quiet moments between observations, as telescopes pause to recalibrate and researchers around the world analyze the latest data, K2-18b continues its ancient orbital dance, holding whatever secrets it might contain close while starlight from its red dwarf companion carries information about its current state on another century-long journey toward Earth. That future light, when it finally reaches our instruments, will tell us about atmospheric changes, chemical evolution, and perhaps even biological processes occurring right now on a world we can study but never visit. The search for life beyond Earth has become more than a scientific endeavor. It has become a reflection of our deepest aspirations to understand our place in the cosmic story. K2-18b, with its dense atmosphere and tantalizing molecular signatures, represents our most promising current opportunity to detect chemistry that might indicate biology among the stars. Whether that promise will be fulfilled remains unwritten in the cosmic script we're still learning to read. As we drift back from this distant world to the comfort of our own familiar planet, there's something wonderfully humbling about the realization that we live in an age when such investigations are possible. For most of human history, other worlds remained purely in the realm of imagination and speculation. Today, we can taste the chemical breath of planets orbiting stars we'll never visit, and search for signs of life in places so distant that their light is older than our oldest stories. The gentle whispers of K2-18b carried on wavelengths of ancient starlight, remind us that the universe is vast, strange, and filled with possibilities we're only beginning to explore. Whether this particular world will answer our deepest questions about cosmic loneliness or simply teach us more about the incredible diversity of planetary environments, it has already earned its place as a bridge between our earthbound existence and the infinite possibilities that await discovery among the stars. The constellation Leo rises higher now in our winter sky, carrying with it this distant world that has captured our collective imagination. K2-18b continues its cosmic waltz, indifferent to our fascination, holding its atmospheric mysteries close while we strain to decipher the faint chemical whispers that filter through 124 light years of empty space. There's something beautifully poetic about the fact that the light carrying these potential biosignatures began its journey when photography was still a novelty and humans had yet to take to the skies. The dimethyl sulfide molecules, if they truly exist in that alien air, were floating through K2-18b's dense atmosphere when our great grandparents were children, when the very concept of exoplanets belonged purely to the realm of science fiction. The investigations of this distant world has taught us that patience is perhaps the greatest virtue in astronomy. Each observation requires precise timing, waiting for the planet to align perfectly between its star and our telescopes. These cosmic clockwork moments occur with mathematical precision, yet they feel almost magical when they deliver new secrets about a world we'll never touch. As we've peered deeper into the atmospheric chemistry of K2-18b, we've discovered that the universe has a talent for creating complexity in the most unexpected places. The dense gaseous envelope surrounding this sub-Neptune world might harbor chemical processes that operate according to rules we're still learning to understand, where pressure and temperature create conditions that exist nowhere in our terrestrial experience. The red dwarf K2-18, burning with its ancient patience, will outlive our sun by trillions of years. If life has indeed taken root in the atmosphere of its planetary companion, it has been granted the ultimate gift: time. Time to evolve, to adapt, to diversify into forms that might be as different from terrestrial life as we are from the earliest microorganisms that first stirred in Earth's primordial oceans. The story of K2-18b reminds us that we are living through a golden age of discovery when the tools of science have finally caught up with the scope of our curiosity. We can now practice chemistry at interstellar distances, reading molecular signatures in the faint absorption lines of filtered starlight. It's a capability that would have seemed like pure magic to previous generations, yet it has become the everyday work of modern astronomy. The gentle irony is that as we search for life among the stars, we're also discovering just how extraordinary our own existence might be. Every new exoplanet studied adds to our appreciation of the delicate balance of conditions that allowed Earth's biosphere to flourish. We are simultaneously more common and more precious than we ever imagined, part of a universe that creates worlds in abundance, yet may grant the gift of life only rarely. The international collaboration surrounding K2-18b research has become something beautiful in itself, a testament to what humanity can accomplish when we combine our diverse expertise and perspectives in pursuit of answers to our deepest questions. From the engineers who built the James Webb Telescope to the theorists modeling exotic atmospheric chemistry, from the data analysts searching for patterns in cosmic noise, to the philosophers contemplating what it means to be alive in an infinite universe. This investigation has united minds across continents and cultures. Whether K2-18b ultimately reveals the first confirmed signs of extraterrestrial life or simply expands our understanding of planetary science and atmospheric chemistry, it has already transformed how we think about our place in the cosmos. This distant world serves as a bridge between the familiar and the utterly alien, a stepping stone toward understanding that the universe is far stranger, more dynamic, and more creative than our earthbound imaginations ever dared suggest. As we prepare to close this gentle journey through the cosmic depths, there's something wonderfully appropriate about ending where we began, with questions rather than answers, with wonder rather than certainty. K2-18b continues to hold its secrets close, reminding us that the universe is under no obligation to reveal its mysteries on our timeline or according to our expectations. The search for life beyond Earth has become more than a scientific quest. It has become a mirror, reflecting our deepest hopes and fears about our place in the infinite. Whether we are alone in the cosmos or part of a vast community of living worlds, the very act of searching changes us, expanding our perspective and deepening our appreciation for the remarkable chain of circumstances that brought consciousness into being on at least one small planet orbiting an ordinary star. Tonight, as you settle into sleep beneath the same stars that shine down on K2-18b, remember that you are living through an extraordinary moment in the history of human discovery. We stand at the threshold of potentially answering one of the most profound questions our species has ever asked, armed with instruments sensitive enough to taste the chemical breath of distant worlds and patient enough to wait for the universe to whisper its secrets. The story of K2-18b is still being written, one observation at a time, one carefully analyzed spectrum at a time, one peer-reviewed paper at a time. Whether that story will include the first confirmed detection of life beyond our solar system remains to be seen, but the very possibility has already expanded our understanding of what it means to be alive in this vast, mysterious, and endlessly surprising cosmos. Sleep well, fellow traveler, knowing that somewhere in the constellation, Leo, a distant world continues its ancient dance around a patient red dwarf star, carrying whatever secrets it might hold through the cosmic darkness, waiting for the next transit, the next observation, the next gentle whisper of starlight that might finally answer the question that has haunted humanity since we first looked up at the night sky and wondered, are we alone